you got a souvenir from how I sound. Not sure if a very nice souvenir, but okay. So I told you how Excel works. It's a very powerful tool. You can use it for anything you want. Okay, but in this case, we're using it to find the solution. And actually, we say, okay, works fine. Then the next step, I say, what happens with depletion? The IPR is scaled down usually. Remember, this is PR. So if you ever hesitate, what happens with depletion? You say PR. If it goes down, then the rest of the curve usually also goes down. Okay. Then, okay, we saw that actually there is some curvature but was fairly okay. And then we say, what happens if we change the tubing size? Okay, and we say, well, this point should be the same because if I'm keeping the wellhead pressure fixed, really, if there is no flow, doesn't matter if I have a big pipe, small pipe, any pipe, just the hydrostatic column. Okay, if I have no flow, really the pipe size doesn't matter. So all of them depart from the same point, but then you have, if it's more flat, it means the tubing is bigger. If it's more inclined, it means that the tuber is smaller. Okay, and usually you want to be, some place where that's not limiting. For example, it's not here, that you're not limiting very much the flow of the well. Okay, because the formation, if it's here, that means the formation can produce much more, but actually it's not producing because you have a very small tubing. Uh, and then you did, just by looking at the plot, you can really say, we just made this qualitative, okay, without any calculation. But we already said if it was worth to use a bigger tubing or not. So that's very powerful. Yes, then the next step, I say, okay, tubing, keep that in mind. The size of the casing is important. The tubing hangers, the holes in the tubing hanger that I'm going to put, due to structural. Then there is one thing, there is erosion. I hope that we reach to erosion. We're going to make one example. Actually, I added to the exercise I had. So I hope we reach to that point. We have to keep below certain maximum velocity due to erosion. Otherwise, we're going to have, it's going to start to eat up the walls of the tubing, and then after you start to eat up, maybe you have corrosion, for example, and then the thickness is going to be reduced, and then the pressure, like the how do you call it, the pressure, the allowable pressure that you can operate will be much and much less. Okay, and like at the end, you might even create a hole, and then you have to replace the tubing. And I told you that actually due to the change, pressure is reduced, okay? And because the pressure is reduced every time you have a bigger volume of gas, therefore the velocity of gas will also be higher. So usually the most critical point in erosion side is at the wellhead, okay? So that means if you don't have problems in the wellhead, then you maybe don't have problems any place in the tubing. Then I told you another thing that you have to consider is if the pipe, if you have some liquids, okay, and this liquid, they can come from different sources. For example, you might have water that condenses out of the gas, or it might be that you have oil that condenses out of the gas, or you might have also that in the formation you have some water that somehow is coming into the well. So that water or that liquid, you have to evacuate them from the tube. Okay, so the gas has to have enough energy to bring it up. And that I told you, that's a very simple calculation made in 1960s by a guy called Turner. He said, if I make a balance in the droplet, okay, what is the force that the gas exerts on this droplet? And what is just by the gravitational acceleration, how much is pulling it down, I can finally, find exactly the velocity that where I have equilibrium of these two forces. And then, we did some algebraics. We said these two have to be the same, and at the end I got this expression, and there were two main things that I didn't know was the diameter size and also this drag coefficient. And I told you drag coefficient measured, they say is 0.44 for turbulent flow. And this diameter, there was a guy in Shell in Delft actually, and he said run experiments, and he found a way to calculate the maximum droplet size. Okay, a correlation also. When you substitute that, you get the famous Turner equation. Okay, and here we didn't say much, but usually your velocity has to be greater than this one. Okay, so for exactly for the same, the velocity will be smallest usually at the bottom hole. Okay, exactly coming out of the formation. That will be because that has the highest pressure. The highest pressure, the lowest, the smallest volume, and then the smallest velocity, right? And then because I have there is the smallest, that's the most critical point for liquid loading usually. Okay, and that I didn't write it here, but maybe you can put a note on your notes. Okay, why? Because the velocity is that's the point usually where the velocity is the smallest. Okay, and if it's going to violate this criteria, then it's going to be there usually. Okay, so just add those to your notes. Then we said, finally, the last thing in this class was, okay, what happens when we change wellhead pressure? Actually shifting the curve. Okay, changing the diameter is scaling the curve. Changing wellhead pressure is shifting it up and down. Yeah, and I told you there are some ways we're going to talk about a bit more, I hope later, we have time. And then we did, okay, then we did the wellhead equilibrium. Okay, and that you got as a homework. I say now we change the point from here to here, what happens? And really not much. We already did the calculation up to here, and now we just have to continue the calculation up there. Okay? If I tell you, well, is the system, you will see now we're going to make one example with pipeline. If I have one more element, I just have to continue with the flow. Okay, co-current. Yes, so now let's go for today. The topic for today. Okay, and today we're going to talk, so just to give you a summary, today we're going to talk about pipeline, and in particular horizontal pipeline. Usually, no pipeline is completely horizontal. You have some inclination. But the thing is that for gas, really the hydrostatic is very, very small. So you can approximate, it's a good approximation to use horizontal pipe for many of these flow lines. Okay, unless you have, of course, maybe 300 meters going up and down. But if you have, for example, changes of 1 meter in elevation, you can really neglect it because really the main pressure drop comes due to friction. Okay, so that's why I think it's important to discuss a bit what happens with a pipe. Okay, so let's see again, our drawing that I guess you are getting tired of making it, but I told you I have to wake you up in the middle of the night and you have to be able to do it. Okay, and now imagine that you have a pipe, and that's actually what you're going to have. Okay, I might be that I have, in these wells from Sasol, they have all the wells producing in one place, and then you have the processing place, the separator some other place. So you have to take it to this place. So you have a long transportation line, might be some kilometers, 50 kilometers, 20 kilometers, whatever, all the way to the separator. That's also very critical for subsea production systems. Okay, there you have always this long flow line. And in that case, for example, the separator is at the top of a platform, of a FPSO. Okay. Yeah. But let's focus now onshore. We are going to neglect this elevation change for now, and just assuming we have a separator, and this line is fairly horizontal. Okay, so okay, so let's go to this tubing equation. P2. Okay. Now I ask you, can I use this equation for an inclined pipe, for any inclined pipe? Yes, right? You don't see why not. Really, the tubing is just an inclined pipe, okay? The only thing is usually it's very close to the vertical, but if I change the angle, If I make it more like 30 degrees or something like that, then I have an inclined line. Okay, so I can do exactly the same. The only thing is I have to determine C and S. Okay, now let's try. So in principle, this equation should also be applicable for h equals 0. For the height, remember h was the height difference. Okay, if we go to the class we had before, just to refresh you about the equation, how it looks like. Okay, we did the deduction, something like this. Okay, let's take that. We say, let's say we put h, because h is the difference between in the z direction, in the vertical direction, between z of 2 minus z of 1. This is what h means. Okay, so we say, well, we just say the 2 points are in the same level. Okay, that means that h is equal to 0, and let's see what are the effects that that has on my equation. Okay, so that means that s, if h equals 0, then s also equals 0, right? You see in the equation here, if h, the height difference, is 0, then this one is also 0. Yep. Then what happens with okay, what happens with my CT? Okay, my CT is all of these things that I have here. Okay, this is my CT. Okay, I'm going to write it again back to here. So S is equal to 0, so that means that my equation, this equation is, so far, is P2 squared equal to P1 squared over E to 0. And that means how much is a number to 0? 1. Okay, so this is 1. Minus QG squared over CT squared. So I have to know now what happens with CT. Okay, and then I almost close, very close to having an equation for a horizontal flow line. So the CT is, I'm going to just to copy from above. By the way, do you understand my handwriting? It's not so bad. Five. Okay, and here we have a problem. And that's what I want to call your attention to. All of that doesn't change, okay? If S equals 0, that remains the same. I have the average temperature, the average deviation factor, so that remains the same. Now the problem comes in this guy here. That guy is going to cause us some problem. What happens when S equals 0? This one equal 1, okay? And that's something we don't want in math, okay? That becomes indeterminate. And then you have here 0, so you have 0 by 1, and that becomes not so nice. So one way that you can do if you want to verify, again, when you're bored, if you're at home, you want to find something to do, you can do it. But remember, there was something in math, and we now to go all the way to kindergarten, that you saw one rule when you have these, I think they're called mathematical indetermination, right? What rule do we have? If we have 0 over 0, 1 over 0, what do you use? Remember? Limits, okay? But limits, we use one technique for that, a special technique. Huh? L'Hôpital? You remember L'Hôpital? A French guy? So you say L'Hôpital, so we use limits first. So we want to say, I want to know how much is the limit of this expression, s e to the s minus 1, 0.5, when s it goes to 0. Okay? No, I cannot. This one is, 1, 0 over 0, so I get problems. So what I do, I use the theorem of this guy called L'Hopital, that he said, well, if you cannot find the limit is also equal to the derivative. If I apply derivative up and down, then I should, if I that's not undetermined, that will be the limit of my expression, undefined. So limit is 0, and then I derive this equation, and how much do I get? E to the s, right? I got rid of the 1, and then this is a sum. Okay, so this is e to the s plus e to the s times s. Yes? Okay. The exponential, when I derive it, is so then that one will be 1, this one will be 1, this one will be 0, and this one will be 1. Yes? And now I finally found the solution. All of that complication, that complicated expression, just gives the limit is 1. That means that the CT for horizontal flow line is just this. No problems. Yeah. Now let's, when in the memory stick I sent you, there is a file that we are going to use now so we're going to make now exactly for the system we had before. Okay, we had a well and we have exactly the same conditions, the well and the tubing, but now we're going to have, instead of very close to the separator, we're going to say it's a bit far away to see how that affects our equilibrium. So we're going to make, so that's a class exercise. Okay, and we're going to make WPR versus PPR, okay? Or we can call it not P, but actually F. And this stands for, we know already PR is performance relationship, right? And F, flow line, okay? Flow line, performance relationship. Okay, and like you're already experts in Excel, I will start doing it, but then you also have to do it very quick, okay? So let's open this file. It's called single dry gas well, okay, and actually that's solved. Okay, that already has what we have done yesterday. Go to data, and that's exactly what we have done, the WPR, IPR, and the TPR. Yes, so now we have to create another column called PPR. Okay, so PPR, and that will be, so what pressure is that? If I have now this system, okay, that is the required pressure I need at the wellhead to flow against separator pressure. Okay, so I just say PWH required. Okay, that will be again in bar. Let's see, in the input you didn't notice yesterday, but we have two. And that's why, because they are planning in this field, they are planning to install a pipeline. And they came one engineer from a company, they send a bid and they say, okay, we propose this pipe with this constant, and you propose this pipe with this constant. And then your boss came to you and said, please, you took the course of this guy Milan, so you have to verify which pipe is best for our system. Okay? So you just need the constant. So let's call it PPR. This will be for CFL1. Okay, that's the constant of the pipe. We can just, instead of, because it might be confusing, so we say for CFL1. And remember, for flow line, horizontal flow line, we don't need this S. So we need just one parameter. It makes our life very simple. So now let's check which equation we have, alt F11. And we have line. Okay, so we have line, an equation called line. Well, actually, we didn't show how the equation looks like. That's something we forgot, okay? if this one is, well, actually we did it, but I didn't put it explicitly. So that means you get P2 squared minus P1 squared equal to, actually the opposite, P1 minus P2, the square root of that is QG. Okay? You get that simple equation, like a quadratic equation. Okay, so you have, again, like always, for the other tubing, IPR, etc., you have three equations. One that gives you rate. Is that the one we need? No, okay? We are not calculating rate. We're calculating pressure at the inlet of that pipe. Okay, so we don't need also P2, we need line P1. So we call that function here user defined, and then say line with L with P, line P1, okay, the pressure at the inlet of the pipe. The C of the flow line is this one. I block it. P2, that will be, what is the pressure at the discharge? Separator pressure, right? The flow line is reaching just to the separator. That I block it also. And then the rate, I just use, if there is, again, I use the same logic. If there is going to be an intersection between WPR and PPR, it's going to be in the WPR range. Okay, so I use the rate, the same range of rate that I had before. This one here. So this is only one rate. Okay, no flow, P in gives me equal to P2. Okay, there is no elevation, so the two pressures should be exactly the same. So that is a good quality check. Okay, and I drag it down. Okay, and actually you can see that the variation is very small. Actually, in that line, you get 40, and if you are at maximum flow, you have 46. Okay, so I'm going to plot it. Bill Gates is messing with the class. Okay, just save it just in case. Okay, so I'm going to plot it, and I'm going to get rid of this IPR and also the TPR, okay, because we're not going to work with that anymore, at least for now. Well, just do something. Save the original file and save this file with a different name, okay? Please, because we are going to do something else with bottom hole equilibrium that I forgot yesterday, okay? So just save it with another name. I will also do the same. Save as, and I'm going to solve just with flow line. I'm going to put flow line at the end. Do the same, please. Don't overwrite the file. Okay, so I'm going to say again, add a new series PPR for P separator equal to 40 bar, and X is going to be the rate that I'm using for all of them is this rate, and the pressure is actually the pressure I just calculate. Okay, and it looks like that. Operating rate someplace, yeah, 2.5, that should be like 2.8. Okay, something like that. Yes. Okay. Here is you have to use line, and I want P1. Okay. Yeah, I'm going to give you some time so you can do it, and also please do it for. Now I plot for the other pipe or flow line performance relationship for P separator equal to 40, CFL2, the second flow line, and here should be the X, and here should be this one. Okay, you see the two? Did you get the same? Still working? Okay, but you see, that there is a difference, and that pipe is significantly smaller. And now you have to make a decision based on how much rate you're going to get over time, if it really pays off to buy this line instead of this line. Okay, this one is very big, probably has almost no pressure drop on that distance. Okay, I'm going to give you some more time that you can finish and compare. Okay, so that this one probably is a flow line with big diameter, and this is a flow line with small diameter. Remember, for both of them I'm using the function line P1. Okay, I'm using line P1. I'm using the CFL of the flow line, either 1 or 2. I'm using the separator pressure because both of them are producing against the separator, and I'm using the same rate. Okay, the only thing that is changing is the C, which is going to give me a different rate. So you will see maybe from this difference is not enough to pay for that flow line. Okay, from this difference in rate, and you have to find out. But usually there are also some other considerations why, how do we define the just like in the previous case for the tubing, there are also some other reasons that how to size gas flow lines, okay, or factors that affect the sizing, factors of gas flow lines, okay, and one of them is the cost, okay. A higher diameter means more material. Remember, when it becomes bigger the pipe, it has to be also thicker to tolerate the pressure. So that means it's going to be heavier and it's going to be more expensive. So higher the diameter, higher the cost, okay, higher the US dollars, and that's why it's it's not so convenient. Okay. You also want to reduce is due to the pressure drop. Okay, you want to reduce the pressure drop, and due to that you also want to is because of that you say, well, a bigger diameter will give me less pressure drop. Okay, there is another aspect that is again related to this liquid loading problem. You usually have, or most likely you have, some liquids coming together with the gas, so you want to liquid transportation. Okay, like for example, if you have a pipe, the pipe is not completely horizontal, but it has some undulation. Okay, when it goes by transport, depending where it is. So in these lower points, if the velocity is high enough, okay, it will be able to carry these small droplets that it has with it, okay, throughout the whole system. But if for some reason the velocity is not high enough, that means I have a very big pipe, then the liquid will start to accumulate at the lower part, okay, of the section. And then when I have that, first I have reduced flow, so this one creates a delta P, okay, and then it might become a day that actually I have pipeline blockage, okay, due to, so these low points, they can create increased delta P, increased pressure drop. They can also create pipe blockage, okay, just because they go up to the whole level and then they cannot go, can induce corrosion, okay. You have water accumulation, and then with water comes corrosion, and you might have some problem on the integrity of the pipe. And you can also have, that's something we're going to talk about it just in a while, hydrates, okay, hydrates. And we will see now what hydrates are, and it's a very critical issue. And also that causes when you know this block occurs, okay, on the pipe, this pressure upstream will start to increase, okay, because the gas cannot flow and it will start to increase. When this pressure is high enough, then it's going to push this slug of liquid. You know one thing, we have the break now in 15 minutes, but my discussion I think will take a bit more than that. Is it okay to take it maybe and a half? I think 7.5 with all of you. None of you is falling asleep. Yeah, having difficulties to stay awake. Okay. So that pressure due to the plug is going to increase until it is high enough and then pushes the whole liquid, and that becomes like a slug. It's going to travel like multi-phase flow. It's going to travel a slug, and then the separator, remember, the separator has a control, okay? The separator, to be ordered to be operating happy, okay, has a level, like I told you, has a pressure, and then both go to these valves that you have here, okay? And then that's fine, okay? That's how it keeps the pressure constant. But what happens if now it comes a big slug of liquid on the pipe, okay? And this volume of this slug is higher, let me put it below, is higher than the volume of the separator. Then you are in trouble. No matter how smart control you have, you're receiving too much liquid, okay? And then the liquid is going to start and coming to the other line. You might have gas going on the other line, and it's messy. You don't want to have that, okay? So that other problem is called slugging, okay? Slugging, and that's a intermittent production of batches of liquid and gas. Intermittent production of batches of liquid and gas. Okay, that's also another problem why we want to keep the velocity high such that it can carry the liquid with it, and I don't have this accumulation and I don't have slugging. Okay, keep that in mind. Very important. Also, an approach that you maybe see is that you, instead of using this type of separator, to if slugging cannot be avoided. Okay, and in many cases, for example, maybe you heard of it. There is a field in the north of Norway called Snow White, Blancanieves. Okay, this field is it's a subsea field, gas field that is 146 kilometers from the coast. Okay, and you have exactly that problem. You have water liquid starts to drop out, and then these slugs happen, and then the separator has to receive these big slugs. That also will happen in block 2. I'm not sure if you know about your neighbors, Tanzania, but they have another field that the same thing will happen. Okay, you have again 80 kilometers, and you have these slugs, and probably in your field, Coral, you will have exactly the same problem. Okay, so you have to take care that the velocity of the gas is high enough to carry the liquid, but also you have to receive these slugs. And the way it is done, you make very long separators. You make like almost like a pipe. Okay, you make very long separators. Okay, that's the liquid level. Okay, you put it's almost like a snake, and then you put another one in parallel, and you put another one in parallel. Okay, and you put like that. You put many, like I think Norway has something like 8, okay, 8 pipes in parallel. And you put here a common entry from a common manifold that is going to give fluid to all of them. Okay, and here I have the production from the field. Okay, and in that way I have a lot of volume and I can receive these big slugs, and I have no problems with my separator. Okay, this separator will be huge if I try to make this separator to receive the slugs that come from the field. Okay, so I do this, and this is called Actually, not a separator, but it's called a slug catcher. Okay. So the conclusion for you is that velocity, gas velocity should be high enough to carry the liquids. Okay. So it's not only about pressure drop, it's not only about cost, it's about that. And then another factor that affects the sizing is the cooling of the fluid. Okay. When I use a bigger pipe, okay, if I look at the pipe cross section, okay, if I use a bigger pipe, I have more area exposed. Okay. Let's say you have here a temperature that is the temperature of the fluid, and you have temperature of the ambient. If I have a small pipe, okay, the area that you're exposed is very small, so you lose temperature very, very slowly along the pipe. If you see, if we plot now, this x is along the pipe, okay, and this is the temperature. Maybe for a small pipe it goes like that, okay, but for a big pipe, for the same starting point, it will go much for a big pipe, okay, just because you have more area exposed, and I guess you know how to calculate that. Maybe we will have, we don't talk too much about temperature in these two modules, but I will see if we have time to have some discussion on temperature. Okay, but basically, the way the pipe usually you have is you have a metal layer. Okay, that's metal, and then you have some big insulation. Okay, so you have these words that you learned in your studies. You have inner convection plus inner conduction in the pipe. Then you have a conduction in the insulating layer. Okay, it might be also that the pipe is buried. Okay, so you have also heat transfer through the earth, through the soil. Okay, and then you have here the soil, for example, and at the end here you have the T ambient. Okay, and if you remember the expressions, how were they for conduction? Okay, you had something like first, you could say that the T of the fluid, okay, minus the T of the ambient is equal to an area, okay, times something called U. How do you call U? Universal heat transfer coefficient, right? Okay, times, well, actually, it's like that, okay? It's the heat that I'm dissipating is equal to A times U, okay? The heat transfer coefficient. And this heat transfer coefficient includes the conduction, convection, also if there is some radiation, it might include, okay? It includes everything in this heat transfer coefficient. And we will see maybe later a way how to calculate. That clear? Okay. So we cool, and you say, okay, that's interesting. The temperature goes down, but why is a problem that the temperature goes down? Okay, condensation, you get more liquid, it becomes a problem. Okay, lower temperature. I'm writing everything down, but maybe you're taking your notes, so just let me know if I'm writing too much. Okay, then you get bored. And lower temperature, more condensation of liquids, okay, which is again the problem of slugging, and it becomes a problem. But also, one thing is that you say you risk forming hydrates. Okay, now we're going to go and talk a bit about what hydrates are, risk-forming hydrates. So hydrates, usually when you say we are at a temperature, at a pressure of 12 bar, okay, and a temperature of 4 degrees Celsius, you see at those particular conditions, you know that the water molecule is like that, okay, O and H. But remember that the oxygen tends to keep all the electrons to itself. Okay, it's a very guy that likes too much electrons. So usually the electrons, and he has two here. So it's a very negative charge. And this one, they end up with a positive charge. So this behaves like an electrical pole. Okay, plus and minus. And what happens when other molecules come here? When water molecules, how do you call this effect? Kind of hydrogen bonding. Okay. Yes. Do you see this any course? I, I guess so. It's yeah. Do you see it someplace? No. Yes. Okay. So that forms that, but then on top of that, when you have low pressure and low temperature, they they start to get a process of solidification, and they start to become more rigid, more and more rigid, and they form a structure that is called they form a structure that is called hydrate that is actually solid. Okay, something like this. It's very difficult to draw it. Okay, so these are oxygen, 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 and it forms like a structure in a special shape. Okay, don't get I have a point. Just bear with me a bit. Okay, but they arrange themselves like in a cage. Okay, when temperature goes down, just because they like each other, they are just colliding, and then when the temperature goes down, they start forming a cage-like structure, just like if they were going to form ice, and then comes here inside, it makes a house. Okay, and this house, if there is some molecule like methane or like ethane or like propane, even butane sometimes can fit in this. Or also, if you have also another small molecules are CO2 and N2, they come inside the cage and they say, we want to live here. This is perfect. You made a house for us. Okay? And this is what we call a hybrid. And it's a solid. Okay? It's like ice with hydrocarbon. Okay? Inside. You hear about hydrates before? Yes? No? Some of you? Okay. And it looks something like this. Where is it? Okay, so that's the cage I try to picture. Okay, the house of this molecule. Okay, that's what it can cause. That's the main problem. Why we are so concerned about hydrogen. Okay, that's what it can cause on a pipe. It becomes solid ice, and then it blocks the pipe. Okay, and that's why we don't want hydrogen. You see, like you say, no problem. Here in Mozambique, if we have a pipe producing from the field, it's always 20 minimum, maybe 16. So we don't have this hydrogen problem. But you will have in these fields that are in the subsea. Okay, you are 1,500 meters down. Maybe the temperature might be 4, might be 5, and then you have to worry about hydrants. Okay, you have to worry about having a good insulation. Hmm? When? Yeah, I'm going to give some tips. Some just this is a very small short discussion, but you have to keep the temperature, so you have to make insulation, very good insulation. Of course, sizing the proper size of the pipe is important, and then you can also do heating. You can put an electrical cable around, but also the most common strategy is to use an inhibitor. Okay, that I will just let you know now what it is. Uh, Okay, so we have the required conditions to form hydrates. Okay, are low temperature. Okay, are free water. You have to have water in liquid phase. Okay, you cannot have water evaporated. You have to have liquid water, or what we call free water. Okay, and what else? We have to have, now we have everything that builds a cage, but we have to have something that comes inside. Okay, so if you have, for example, a heavy hydrocarbon, heavy chains, they don't cannot go inside because it's not big enough for them. So you have to have a small hydrocarbon molecules. Okay, these are the three conditions that are required to form hydrates. And just like a side note, okay, so the formula for hydrates is 4CH4 23H2O. Okay, so you might think, okay, so it's a lot of water. So, okay, it takes only a bit of hydrocarbons, so I shouldn't be so concerned. But if you put fire, if you put a match on this block, it's going to burn. Okay, and why? Because I will show you now it's a big amount, even though it has only four moles of methane. That's a huge amount for that place. So let's make a very simple calculation. The molecular weight of that is, remember, water is like 18, right? And there you have 16, so that gives you more or less 478, the molecular weight, kilogram per kilomole. And the density is almost like ice. Okay, so the density is very simple and doesn't change with temperature, doesn't change with anything. So it's like around 900 kilogram per cubic meter. Okay, so now let's calculate. If we take a cubic meter, very interesting, a cubic meter of hydrate. Okay, let's see how much methane that cubic meter has. So how I make that calculation? How much methane in a cubic meter of hydrate? Okay, and actually the hydrate of methane is called methane clarate. Okay, clarate. I don't want to give you chemistry, but it's just this is interesting. So how much methane? 1 cubic meter. First I calculate the mass. Okay, so the mass is equal to the density times the volume. Okay, and that's 900 times 1. That gives you 900 kilograms. Okay, and then I divide by, to know the number of moles, how many moles of this I have. Okay, so I divide 900 kilogram by 478, and that's how much? How many kilomoles? 1.88 kilomoles of hydrate. Okay, and then how many moles I have in a kilogram in a kilomole of hydrate? How many methane moles of methane do I have? Times 4, right? Okay, so that gives you N of CH4. It gives you 7.53 kilomoles of methane. Okay, and now how many, we remember, we are petroleum engineers, we don't like these moles, mass, we're going to get fired, so we have to change very quickly before the manager comes to standard cubic meter per day. So how do we change? We had one equation, remember, B standard conditions is equal to N times, remember the name, 23, the number, 0.67. Yes, so how much is that? How many? 178. Okay, standard cubic meter of methane. Yes, yes, I am not impressed. Okay, so now let's see how, if we want to store that amount of gas. Okay, this block I can take it, I can put it any place and it will have that huge amount of methane. Okay, at standard condition I have a block, and that block represents 178 blocks of methane. Okay, so how much will I have to, what will be the pressure? Okay, now imagine that I have methane, not as hydrate, but just in gases, in gas. Okay, what will be the pressure that I have to have this methane to have the same 178 cubic meter? Okay, standard cubic meter. if I put it in a tank. Okay, what will be the pressure? And the pressure is, yeah, I'm going, the pressure will be the same number of moles, okay, 7.53 times R times T at standard conditions, okay, because I'm storing it in a tank in the surface and in 1 cubic meter, and that gives you 180 bar, okay, huge. That means that if I have this block of 1 cubic meter has the same amount that a tank of 1 cubic meter at 180 bar. Okay. So that's what some people say. We have some guys at the university saying we can really use hydrates for transportation. Okay, it's a very efficient way to transport things. And it's low pressure, it's just a solid. So that really I can put it even to atmospheric pressure. Okay, but it's huge. Okay, even though it has a lot of water, it's huge the amount of methane it has inside. Okay. So that's just a very short example. But now going back to hydrates. So in hydrates we have, if we look at the diagram called PT, okay, PT, we usually have what we call a line called the hydrate formation line. Okay? And if we are inside, here you have risk of hydrate formation. Okay? And here you are risk free. Okay? So what happens usually in a transportation line, okay, we have in the transportation line here we have P wellhead and T wellhead, okay, and then we want to go to P separator, okay, and the temperature is also P separator is not here, but P is in this axis, so P separator, okay. So if I have a very good insulated pipe, it's going to end up here, fine, no problem, okay. But if I have a poorly insulated pipe, it's going to end up here, and then I have a catastrophe here, exactly when it crosses this hydrate line, okay. All of these long exercise, long explanation is to show you that you have to be careful with the pipe size, okay, in the insulation of the pipe. Okay, otherwise you can have the formation of hydrates someplace in the pipe, and big issue, it can actually plug the line, and then to fix it is a big job. Okay, it has to do it very carefully. There are some methods we are not going to cover here, but it's complex. Okay, so the way to deal with that is we use usually hydrate inhibitor. Okay, remember what we discussed about the molecule that is HOH. Okay, if you have only water, they are going to just accommodate itself and they're going to be happy and nice. But then you have to come with something else that is also very polar and is going to interfere with the formation of this cage. Okay? And that we use another very polar molecule, for example, methanol. Okay? OH. This one, again, you have an oxygen. These guys are a bit egoistic, so they say, I want all the electrons for me, and creates, again, a dipole. And that interferes with, so that's what we call using hydrate inhibitors um, to change the hydrate. We are just going to take a break. Just wait. We are almost going to take a break. Hydrate formation line. Okay, and that means if I have an inhibitor and I inject it, actually I have to inject it, and you will see I have to inject it with the flow. So I have to inject it usually the way I do it at the wellhead. Okay, so I have to send inhibitor, and if the original hydrate line was this one, and what the inhibitor has, if I increase, for example, some concentration with inhibitor, okay, as I increase more and more and more, the inhibitor is actually reducing the hydrate area. Okay, and then doesn't matter if it's good insulated or not, I'm safe. Okay, so that's the effect of the inhibitor. Okay, in a PT diagram with inhibitor. Is that clear? Yes. Okay. So now we take our break, more or less. So the point to convey here, temperature goes down, but when we have low temperature, when we have a risk to form hydrates, and we have to inject this inhibitor that is called methanol. Okay, methanol, or also TEG, triethylene glycol, or MEG, monoethylene glycol. Okay, these are the inhibitors that we normally use, and we have to inject them at the wellhead. Yes. So we will see now how that's done usually. Let's take a break. Let's say 20 minutes, and then we come back with the rest. Yes. So I just wanted to give about the size of the pipe, and we went into this discussion on hydrates, but basically the cost, the delta P, the has to carry the liquid, and also the problem with heat transfer and hydrate. Okay, we want to avoid hydrate. It's not a problem for onshore. It's not a problem for shallow, but it's a problem for deep. When you go for deep, it might be a problem. So in that case, you have to inject methanol, and what you do on the tree. Okay, let's say imagine that you have now a subsea system. Okay, gas well that is producing, let's say, to shore. I'm not sure. I think in coral it will be producing to an FPSO. Okay, FPSO. I make it very simple. Let's make the theme, and here I have okay my well. That goes up. Okay, to the separator. Yes, so I have to inject this inhibitor, and as a problem might happen here, someplace in the line, I have to be sure, and I have to send it to the place where it starts to cool down, because it might happen any place in the pipe. So what I do, I send another pipe from this FPSO down. Let me use another color. Okay, I send another pipe down that has many other things besides from inhibitor, and I inject it actually here, okay, with a valve. So that's the inhibitor line. And you can see why it's expensive, because you have one line that comes from the well, but then you have to send one line partly to inject this inhibitor, this methanol. Okay, and this line usually is what you call an umbilical. Okay, and the umbilical is like a flexible pipe that has a lot of bunch of other pipes in between. Okay, so an umbilical, the cross section of an umbilical, okay, for example, is something that's not so round. So let's try to make it a bit better. Okay, in the center, it has the methanol line. Okay, then to the side, it has the hydraulic line that you use. Let's use another color. Remember that we have to operate. We have to be able to open and close the wells. Okay, and we can send either a robot here. We can set an intern from a master student that making the thesis to make it here. But if this is too deep, 2,000 meters, then the student is going to be in trouble. So you have to send to do it with the hydraulic line. Okay, and then you have some other small lines in between. Okay, that they can carry power, small power. They can carry fiber optics to transmit sensor data, etc. Okay, so it's a pipe that is flexible. It can bend, and it has all of these things inside. Okay, the methanol, etc. We call an umbilical. Yes. Yeah. So that I think I'm going to skip. I wanted to show you how the subsea system looks like, but I think Yeah, I think we can just try to do it. Just put some in. I think that's also interesting. So you have the tubing hanger. Okay. You have below here. You have this the downhole safety valve, DSV. Okay. And you have here one line that goes inside and actually goes inside this hydraulic line. Okay. And after I come up here, I have this PMV that is called the PMV stands for production master valve. Okay. Then here, exactly here, is where I inject the inhibitor. Okay. And the inhibitor, I have another valve. It is a control valve that I call MIV. MIV stands for methanol injection valve. Okay, that's to control how much methanol I want to inject on that particular well. And after the production, I have, what do I have after the master valve? Wing valve. Remember, it's like religion. You have to say it, 5 times a day. Production, wing, choke. Production, wing, choke. Okay. Then comes the wing valve, PWM, PWV, production, wing valve. By the way, did we put the recording? Then after that, I usually have, this is a flow diagram of a subsea well. Okay. Then after that, I usually have a PT and a TT. That stands for pressure transducer and temperature transducer. PT, pressure transducer. PT, that's temperature transducer. Okay. What do I have then? After that, the choke. Okay. But the choke usually is something that you saw from the picture. It's something that has very small holes and very high velocities. So, what is the problem with that? That we saw just already yesterday, that you can have erosion, okay, in these holes. So it's something that eventually I might have to change many times during the life of the well. Okay. So what I do, I make in a separate module, I put the choke in this separate module such that I don't have to mess up with this one. I don't have to change that in the tree. I have this in one module, and the choke, it has its own separate module such that when it goes bad, when I have to change it due to erosion or something, I can just retrieve that module and leave the rest of the tree tranquilo. Okay? So here I have, usually in the choke module, I have SD. SD stands for sound detection. Okay, then I have another thing here that is MPM, multi-phase meter. Okay, and then here finally I have again a PT and a TT. Okay, then I have the choke, and then I have another PT and TT. Okay, and then I have another thing that actually blocks the okay, so this is the choke module. This is what I have here, and the idea is that I can just retrieve it and I can change it as needed. If something goes bad inside, I can retrieve it. So that's the choke, also called the choke and metering module. Okay, let me make more space. Okay, yes. And this methanol line, I have here another valve, okay, that is called the methanol injection valve, and I'm not sure exactly how this one is called, but it's just on off. Okay, this is something that I can regulate, and that one is on off, and that goes exactly through the same port, and that goes exactly through the same port. Okay, that line. But this line, fluid is coming out, and this one is methanol coming in. Okay, so let me again. I have is I'm not a very good planner on the where to put my things, so it's good that I have this tool that I can rearrange. Otherwise, I will be in trouble. Okay, that's E in. Yes, so it's more complex. You have the point here is more complex. You have to inject the methanol exactly here or the inhibitor exactly here, and sometimes you don't have only methanol, but you have all other things. You have scale inhibitor, a demulsifier. You have demulsifier, scale inhibitor, hydrate inhibitor. You have wax. Okay, remember these heavy chains that I told you, these heavy C's that they tend to also come out of solution. So you also have to inject something to avoid wax. And then you have a lot of lines here, okay, that have to go through it. Okay, so now, for the last part of the class, I think we have to do two things. Going back to our topic, we have to investigate. Remember I told you, okay, that CT, okay, going back to, but let's look now, we're going to look at two things. We're going to look at the, um, let's call it better estimation of CT, okay, of the tubing coefficient, and then we're going to talk about pressure traverse. Okay, so far we said we treat the tubing like a unit. Okay, where you have an input and where you have an output. But sometimes you would like to know what happens along the tubing. Okay, not only what happens in and out, but just how the pressure looks like along the tubing. And that might be to detect problems. For example, you have some scale accumulation someplace in the well. Okay, okay, might have some accumulation, something restricting the flow. Okay, and let's say you test that well and you say, well, it's producing much less than what it should. Okay, so what's happening here? So sometimes what is done is you come with a wire, okay, you put it inside and you start lowering down at different levels, okay, and you measure the pressure, okay, and then you get a curve that tells you pressure, sorry, that will be pressure, okay, and that will be TVD from 0 all the way to um, bottom, okay, the bottom of the well, and it does something like this. Okay, pressure is higher at the bottom of the well and pressure is lower at the top. And then you say that's what I should get, and then for some reason, let's say you get exactly the same, but then you have here a big drop. Okay, sorry, it will be a higher pressure. Okay, so that's what you calculated with equation. Okay, and when you do the measurement, actually it goes here, it goes pretty well according to what you expect, but here has a jump and then continues down. Okay, so here this is the measure. Okay, and you see that there is something wrong there. So that's, for example, that's why we want to look, and that's called pressure traverse calculations. Pressure traverse calculation. Okay, and basically it's the pressure distribution along the tubing. Okay, and it's very good tool for diagnose. So now let's first do, and that's related also with CT, okay? Because remember CT, we're estimating for the whole tubing. If we want to make it for different sections, okay? what we are going to make is we are going to subdivide the tubing in small tubings, okay, in small segments, using the same equation, right? Sounds logical. You have the same equation applies for the big tubing and the small tubing, okay? But now I have to calculate properties for each interval. Yes? Okay, so that's what we are going to make. So first, I suggest we go to our, okay, not to this exercise, but to the original, not the flow line, but the one I told you to save a copy. Okay, it's this one here. Okay, and we had this intersection. Okay, let's remove WPR from here. Don't care, and we have IPR versus TPR. Okay, but this TPR, okay, I did it. I had a CT. Okay, and if you remember, CT was a function of average, a deviation factor, and average temperature. Yes, if you remember in the equation, um, is where are the notes here? We have written quite a lot. Okay, so if you remember in this equation, the CT depends on the C average and the T average. Okay, and at the same time, the C average depends is a function of P average and T average. Yes. Okay, so that means that this CT is somehow affected, is a function of the P average that I assume. Okay, and you will see now if you go to the Excel sheet, where did I take that C of the tubing from? So you go here to tubing constants, and you see I calculated here for you using some data what will be the C, the CT, and the S. Okay, 0.155 and 425. These are the numbers that we have been using. Okay, but you see what did I use for that? I use an inlet pressure. I assume I didn't have it. Okay, I didn't calculate it from before, so I used just reservoir pressure, guessing. That is wrong. Okay, but that was just a guess. And outlet pressure, I assume separator pressure. This one was a good approximation, but that one was not. It's way off. Okay, so what happens now? What if I want to make my calculation better? Okay, I want to make a better TPR. I suggest, okay, we already have, okay, what was the bottom hole pressure? Or let's see how does it change. Okay, bottom hole pressure will be bottom hole pressure we said will be between between here. No, the bottom hole pressure will be here. Okay, how much is the bottom hole? Was 84, right? I think the operating bottom hole pressure. I think we have calculated the other day was 84 something. Let's use very quickly the solver. Solver, please drive this value to 0 by changing, no, by changing this number. Okay, okay, so that gives me 84. Okay, so actually the bottom hole pressure is not 304, but it's 84. So let's see now what will be the effect of this pressure in my CT. Okay, so we now copy this pressure 84 to the tubing constant, use it as the inlet pressure. That's the real inlet pressure to the tubing. Okay, so let's paste it there. And now instead of getting 425, okay, 4 got 419. And instead of getting S155, I got 151. Okay, so I can go and correct again my curve. Okay, see, okay, I'm using the wrong CT. I'm going to now copy this one here, paste value. Okay, 419, and instead of using 155, I'm going to use 151, the elevation coefficient. How the curve change? Did it change dramatically? Not much, right? Let's see what is the new equilibrium point. Well, it's very close to 84. Let's run the solver again to see. Okay, 85. Okay, engineering purposes of the point I'm trying to convey here is that yes, we made a wrong assumption for the pressure at the inlet, but really doesn't affect that much my calculations. Okay, affects by some percentage, but not much. Some other effects are more important to capture. That clear? Yes? No? Repeat? Yes? Okay. If you remember, okay, with this CT, for CT that is all of these in front of the equation, okay, we needed an average deviation factor and an average temperature. Yes? Okay. The average deviation factor, the average temperature, okay, I measure. I know how much is reservoir pressure and I know how much is wellhead pressure. That I use and I know. Okay. But the pressure, I don't know beforehand. I have to have the CT to make the intersection to have the pressure. Okay. So I say, let's assume a number for the inlet because I have the wellhead pressure, and let's assume a number for the inlet pressure. Okay. I'm going to assume reservoir pressure. Okay. But then I have to verify that assumption. So I went here, and here you have that equation, exactly this equation program here, okay, in this part. You didn't have to do it, I did it for you. Okay, and this is all the input I'm using. The length doesn't change, the ammeter doesn't change, gravity doesn't change, temperature doesn't change, the wellhead pressure doesn't change, but the inlet pressure I have 304, okay, reservoir pressure. I don't know how much it is. I have to have the curve first, find the equilibrium, and then then I have the pressure. So with this number, reservoir pressure 304, I get 425 and 0.155. Okay, these are the numbers that I was using in my exercise. Yes, okay, and that gave me an intersection of, if I solve again, sorry, it should be 0.55 and 4.42500. This gives me an intersection of 84.37. Yes? Okay. Now I have the pressure, and I say, wow, the value that I assumed before to calculating the CT was way off. I was assuming 304. Okay, and it turns out it's 84. It's a big difference between these two numbers. So I want to see, now to make the calculation better, say I go back to my sheet, okay, and I say, instead of using 304, I'm going to use 84. What was the number? 84.378, okay? So I'm going to use that 84.378, okay? And that should be my real CT, okay? Instead of 425, 419, I copy that number, paste it here, in tubing, okay? And then I also copy the elevation factor, that also changed, because that also has inside this set, this average set. Elevation, paste, okay? And now you see 84.37 doesn't give you 0, but it gives you 0.7 bar, a difference of 0.7 bar. So we run again our solver, okay, and really I'm still getting the same equilibrium rate. That means the curve didn't change much, the TPR didn't change much. Okay, so the point I'm conveying is, I'm trying to convey here, it's, okay, so let's put that discussion below. When using the right value or a better value, okay, because it's not the right is 85, but we are using a better value when using PR has P in, okay, to estimate P average. Okay, that means 304 plus 40 divided by 2. I obtain a CT of 425.00 standard cubic meter per day per bar. Okay, and this S is 0.155. Yes. Now I repeat my calculation. The equilibrium point, the equilibrium PWF is actually 84.378 bar. Okay, that is way different than 304. Okay, okay, using this pressure, this average pressure, okay, P average now will be 84.378 plus 40 divided by 2. I obtain CT 419 something. Okay, it was not a per bar, and I obtain S equal to 0.151. You will say dramatically different. Okay, there is a relatively big difference between them. However, this doesn't affect my equilibrium. However, the equilibrium point is not affected dramatically. Okay. Yes. Clear the point? Maybe it's very easy to make. Okay, just change the numbers, but keep that in mind. Okay, that even though I made an assumption and I afterwards is that I calculate the pressure, really this assumption doesn't have, usually in most cases, doesn't have that big of an impact. Okay. Yes. So now let's go to this pressure transverse. How we are going to make this calculation? And this was just a comment to say this was just an example. Well, with scaling, so just traverse calculation can help diagnose a well with scaling. Okay, because you see what you should get. You should get this pressure profile, but then you obtain a different pressure profile, change this one place, and then you know that's where I might have a problem. Okay, and that's what I want to focus now on the last part of the class. I hope we have time to try to see, to tell you how to use this tubing equation to calculate pressure along the tubing, not only at the inlet or at the outlet, but also in the intermediate. Okay, for that I recommend you open the Excel sheet called, so this one we can close, we abandon that, and we go to the next one. Sorry, it's pressure traverse dry gas well, not this one. Okay, and I did some homework already here for you. Okay, we have to fill a lot of things, so let's see if we have time. But let's see first what I have done. Okay, first I have said I included the variable called TV. Well, here we have all the input. Okay, the properties of the tubing, length of the tubing is exactly the same well we had before. Okay, nothing has changed. The same specific gravity, wellhead pressure, flowing bottom hole wellhead temperature, wellhead temperature, bottom hole temperature, reservoir pressure, etc. Okay. And okay, and what I have done, okay, what we are going to do to solve this problem, we're going to take the well, okay, that's the wellhead, and that's the flowing bottom hole. Okay. And I'm going to say it is made out of many tubings, okay, many small sub tubings. This tubing is made, and here I'm using 10, okay, 10 intervals. I say each one of them has certain length, delta L, okay, and I have to compute for each one of these intervals. If I want to calculate, okay, let's go, we already know this wellhead pressure is constant and is equal to 40 bar, right? And we know that the equilibrium rate, how much was it? 2.85 e to the 6th, right? Standard cubic meter per day. That was the equilibrium rate. So now I'm going to say, if I calculate this CT and this S, okay, I can use just the tubing equation, right? And I have P2, I have the rate, and I can calculate P here, no? PI. And then I move to the next segment, CTS, so that will be CTS1, CTS2, CTS2, and let's call this pressure, we also can call it P1, okay? P2, and then I do the same P3, then CT3, S3. Yes? You got the idea, the principle. We just use the same, the strategy, you know, I told you, works for everything. Divide and conquer. If you don't know how to attack the problem, divide it. And then you try to solve the small parts of the puzzle. So I ask you, why we don't start from here, from the bottom? We don't have the pressure, okay? Here we have a pressure. We know this pressure is constant, and we know the well, when it's in equilibrium, should operate at that, okay? So our task here is to calculate the pressure distribution along the tubing for the equilibrium rate, okay? That means that CT cannot be an input. Now I have to calculate for each one of the sections the CT and the S, depending on, and we're going to do it now. And I'm not sure if you want to do it yourself, or I'm going to try to do it slowly, but then you get it as a homework and you have to work on it, you know. Yeah, you prefer that? Yes? Okay. So let's see first what I have. I already have made, remember, true vertical depth. That's how the coordinate system we usually use is TVD, and this is 0, okay? This TVD stands for true vertical depth, okay? And in our case, okay, and you see the difference between that and MD, okay? MD stands for measure depth, okay? So if, for example, depth, so if, for example, the well is deviated, okay, and you want to see the MD here, MD and the TVD at that point, okay, which one is going to be bigger? The MD, okay? So when they are not the same and MD is much bigger than TVD, that means that the well is deviated, okay? When the two of them are the same, means the well is vertical, okay? So I have here, this is a vertical well because if you see up here, tubing TVD and tubing MD, they are the same, okay? So I have done divided in equal elements, okay? To get 11 points. 1, 2, 3, these are 11, right? Yes, 11. Now the first thing, remember, we need a bunch of things for the CT, but we need mainly the temperature of that section, the average temperature, and the pressure, okay? The temperature, we have the two temperatures, 378, let's see how much is that in Celsius, minus 273.15, 104 and 80, so from 805 to 89, okay? So we have here at the bottom hole we have 105, okay, the temperature, and then up here we have was 89, right? But what happens in between? Okay? We don't know really yet. Okay, we haven't talked about how to calculate temperature. But I suggest we make just a straight line. We have these 2 points and we have a straight line. Okay, how do we interpolate or find for every position? Remember, I have now a discretization, and I want to have for every section, I want to have its temperature. Okay, so how do I do that? Linear interpolation. Okay, you know it's so it will be, if I refer it to here, this is my TVD. Okay, it will be 105 minus 89. Okay, divided by that's the TVD total. Sorry, that will be, okay. Let's call this one the final depth. Okay, TVD star. TVD star minus 0. Okay, this has to be equal to 105 minus the temperature that I have in that position and a particular position TVD divided by TVD star minus TVD. Right? Linear interpolation. Yes? Clear for all of you? No problem? Okay. So I have already programmed for you that function, so you don't have to worry. And that's what I'm actually doing here, doing this linear interpolation. So I want to calculate the average for that section. Remember, the C is using the average temperature. So I say the average will be one from the next point plus the one from the current point divided by 2. Okay. I do the same. So I have a T average for all sections. Actually, if I have 11 points, I have 10 sections. Okay. Yes. Now comes the tricky part. I have to assume a pressure. Okay. Because I don't know. I have to assume to calculate the CT. Okay. So which pressure? The pressure, actually, the pressure at the wellhead is 40. Okay, I should have it here someplace. Then we have to go down. If you remember, what was the pressure? 86, right? We calculated with the equilibrium. 84.378, right? That was the flowing bottom hole pressure. We're working with the same well. 84.37, yeah. So we have to go from here to there. How do I do it? I can use, we have 10 intervals, so I suggest saying, calculating first a delta P will be the pressure at the bottom of the tubing, 84.368, minus the pressure at the top, that will be 40. That I divide by the number of sections, okay? Divided by, I'm using 10 sections. That will give me a delta, and that's assuming that you lose the same pressure in every segment. Okay, I'm not sure if that's correct. That's an assumption. I'm making an assumption. Okay, so I will say this one minus, oh sorry, plus this one. Okay, you can use here any number you want. I'm saying I know the pressure from my previous analysis is 84, so I'm going to say that you lose the same pressure in every segment. I will see now if that's correct or not, but that's my first approximation. Yes? Okay, from our previous, let me just recap. From the equilibrium analysis, PWF of equilibrium was 84.378 bar, right? Yes. And P wellhead is 40 bar, yes? So I'm going to assume I lose the same pressure in the same amount of pressure in every interval, okay? So that means I assume delta P is a constant. That's an assumption, okay? I have to verify it later, but that's an assumption. Delta P is constant for every section, okay? That means I have to go from delta P will be equal to PWF of equilibrium minus P wellhead divided by the number of sections. Okay, that means 84.378 minus 40 divided by 10. Yes. And if I sum from 40, that number I should get, if I, we have our math correct, my brain is still working okay, then I should get at the end what I should get here? 84.37 something. Okay, exactly. My brain still works. It's not too late. I have that pressure for every point. Okay, I have the temperature for every point, but I need the average for the section because that's what CT is using, the average of the section. So I will here exactly the same. This plus this one divided by 2. Next, plus the current divided by 2. And that I don't need because I have only 10 sections. Okay. Now comes the critical part. For the CT, I need this average temperature. I already have it here. And I need the average C factor. Pressure is not in that equation. It's just the C factor. Okay. So for there, I'm going to call this function that you used the first day, C factor standing. That function receives pressure. Okay. The average pressure receives the temperature, but remember the temperature, it was in Celsius. Okay. So we have to subtract 273.15 because the temperature was in Celsius. Specific gravity of the gas, that's here. I block it. And the unit, remember, was 2 for SI units. Okay. This is the deviation factor. Okay. Got my C average for every section. Now I want to use to calculate the elevation coefficient. The only thing that I need to calculate pressure is these two guys, okay? I need the elevation coefficient and I need the CT, okay? So I have already programmed for you two functions, S, or let's find it here. I think it's better if we go here. These are defined. And let's look for, it was called S, I think, no? S here. And S is taking the specific gravity of the gas is up here. I block it. Taking the average temperature is here. I don't have to block because that I have to change. That will be different for every section. Okay. The C average and the H. What is the H of each section? Oh, here is tricky. It has the height, okay, of each section. So that means what I'm going to say is this TBD minus the previous. Yes. Do you agree? The height, set the elevation or the TBD of the lower point minus the TBD of the upper point. Okay, and I got, remember the number I had for the full well. How much was it? 0.155. This one is an order of magnitude less than the full well. Okay, then I just drag it down. It should work. Okay, so it's the same for all segments. Okay, the set is not much. And then CT. Okay, CT, I also have an equation. Let's see. CT. CT. C flow constant. Okay. And let's see, that's taking a lot of things. So that's taking diameter, tubing ID. I have it here. Block it. Specific gravity of the gas here. Block it. Friction factor is here, block it. The average, I'm going to take it from each section. The average, take it for each section without blocking. The length, what is the length? It's vertical, okay? So it's also this minus this one, okay? It's exactly the same as the height. It's this one minus this one. And S is also using S, and we have it here. Okay, remember how much we had for the full well? 42,000, I think. Okay, and now we are getting 130,000. And that does that make sense? Well, yeah, because the pipe is much shorter. So the pipe really, if I put a certain pressure drop, is going to give you much more rate than a longer pipe. Yes? You. Okay, finally, if we didn't do any mistake, we calculate the CT for each section and the S for each section. Okay. Now we start calculating the pressure. What is the first pressure? Separator pressure, okay, 40. Then to calculate the next, which equation do I use? Tubing, okay, the tubing equation. But we have three of tubing. Q, tubing P1, and tubing P2. Which one do we use? Okay, we want the pressure at the inlet of that section. So we say tubing P1 is CT of the section, is the S of the section, P2 is this one here, okay, and that I shouldn't block. That one I block? Do I block or I don't block? No? Why? When I drag it down, it should take the one from the previous, okay? Yes? So I don't block it. And the Q, would that be different for every section? Every section is flowing the same gas, right? What comes into one section comes out of the section. So the Q is constant. So that one, I should select it here and block it. It's constant for every section. Okay. 46, then we go down all the way to, okay, 40 to 85. Yes? Okay, and you see actually, if I do it like that in parts, actually I found a different, slightly different value than using it in one segment. Why? Because remember, the tubing equation assumes that the properties don't change much. But when I discretize, actually there is some variation and I'm capturing much better the delta P. Okay, but you see the difference practically is not very much. Yes? Okay, so that's the homework. Okay, you have to repeat it yourself and yeah, repeat it and do it as homework. Okay, and the pressure, that's how it looks like. Okay, it has some curvature, but it's relatively more or less linear. Okay, in that case, it behaves almost like a, like a liquid. That clear? Yes. Okay, more or less clear. Okay, so let's summarize. What have we? What? Not today. Not you are not yet done yet. We still need some minutes. Okay. What we say, we want to calculate pressure along the tubing, okay? The variation is important. We want to know, because we want to know what part of the tubing has a bigger pressure drop. If we are getting more pressure drop than what we should, we want to do troubleshooting for all kind of reasons, okay? So we say we want to run calculations. To know the pressure, I suggest we cut the tubing into small parts, smaller intervals, okay? In that case, 10 intervals. And we say, well, each one of these interval is almost like a small tubing, a shorter tubing. The only problem is I have to calculate a C and an S for each one of these segments. I cannot use one for all of them. I have to use one per each. So first, so what we did first I already gave you the depth, okay, and the temperature of each point. So first I say I want to assume a pressure because I don't know what pressure each point has. That's what I have to calculate. But the CT and the S, they require a pressure. So I have to assume, okay, to start with, to assume a number. So here I'm assuming actually I have the same pressure drop in each section. Yes? And that's the assumption. I did it calculating this delta P, and then I say this one is this one plus this delta P. This one is the previous plus that delta P. Yeah? And then I calculate the P average in each section. Okay, the P average and the T average. Now I have everything I need to calculate C and T, CT and S. Okay. Well, I need the, where is the equation? Okay, that's the equation. And S, I need C average. I don't need pressure, okay, but I need C average. And to calculate C average, I need pressure. And here, I also need C average. And to calculate C average, I need pressure. So I calculate C average using this P average and this T average, okay, of this section. And then after that, you say, well, I have to program this ugly equation that has many things inside, and I have to take care of the units, etc. But I was nice and I gave it already to you, okay? So you don't have to think about it, about the units. I calculate C and T for each section. So each section is its own tubing. And now I depart my calculations from the point where I know the pressure, okay? The wellhead pressure. And I know the rate, and I move from wellhead pressure 284 meters down, calculate that pressure. Okay, now I move. I have this pressure, and then I move 280 something meters down again, and I calculate that pressure. Each one using its own CT, its own S, and its own inlet pressure. And you see actually that the CT doesn't change that much with every section. Okay, might be some variation, but not much. Okay. 242. So I have still, I wanted to go. You have a lot of things here, but the next step is that you have pressure in every point. You have temperature, so you can calculate the VG, and you can calculate the real gas velocity in every point. Yes, and when you have the real gas velocity, you can calculate this erosional velocity and Turner, and you can compare. Okay, but I suggest. I think you're tired already. Keep it for tomorrow. What do you think? Or do you have energy to continue? No, you're already depleted. Okay. How to find the D? No. T. T. This one. Well, I just say this one is the average of this one plus this one divided by two. If the is the average, okay, of these two. Okay. I just gave you, but it's a linear interpolation. I'm just saying I have this temperature, I make a line in between. Okay? Yes, give it some thought. You will, if when you do the exercise, okay, so let's write that down, okay? So that's the other, I'm going to copy that line. I'm not sure that's a solution, okay? Maybe I made a mistake here and you'll get a different solution. But I hope this is the right solution. Okay, so that's this, and let me put the graph also, P versus depth, how it looks like. It has some curvature, but it's almost like a straight line. Pressure. Okay, so there's like homework, okay? Homework that is going to have homework. Solve this exercise by yourself at home. Okay, and the exercise is basically find P versus TBD for the well studied in class. Okay, for PWH equal to 40 bar and Q of the gas equal to 2.85 e to the 6 standard cubic meter per day. Okay, find TBD, that's the main goal. Okay, versus depth. So it's exactly do the same that we, and I'm going to talk tomorrow a bit about the other part that we didn't discuss, that we have to compute, and that's going to be very important to, I want to discuss it because that's what we do actually when we have multi-phase flow, okay? The pressure drop in multi-phase flow depends also on the local velocities, and there you have gas and liquid. Okay, so you have to do exactly the same procedure, but more complicated because it's we have two phases, liquid and gas, and we have to have a density for the gas, a density for the liquid, two rates, etc. So it's going to become messy. So I think if we attack it soon in this exercise just for gas, you have your mind already prepared for doing the multi-phase. Okay, but that's the next step for tomorrow. For tomorrow, we are going to calculate the local rate using VG. Remember, it's just a multiplier. Standard condition rate to local rate. And then we have the local rate. We calculate local velocity. Okay, and then we use, we compare it with the erosional velocity to see if we will have problems. Yes, so now let's close the session. Let's see what, a very quick summary. We say we derive the equation for the horizontal flow line. Okay? It was a bit tricky, but we managed. It's just a quadratic equation, and we did the equilibrium with that flow line. Actually, with two flow lines. Two engineers, one from one company, one from the other. They were selling these pipes, and then we say, which one do we take? We realize, okay, there is a difference, but really not much. I told you some of the problems that you have when you have a big pipe or a small pipe is the accumulation of liquid, is the losses of temperature, that you start losing a lot of energy because you have a big area, and that can have a problem like slugging, and that can give you problems like hydrates. I talk a bit about hydrates, what hydrates are, and it might be relevant for your fields in Coral, in this deep area of Mozambique. And that's not so important. I told you that usually we inject an inhibitor to avoid hydrate, and that means adding on purpose. I am adding liquid to the system on purpose. Okay, so even if it's very dry gas, it still has some water coming out, so I have to inject the inhibitor, and that makes it multiphase. And then we went to the last part that we said actually, well, when you calculated CT, you assume the pressure. Okay, and we wanted to see how that assumption affects the equilibrium point. Okay, so we assumed reservoir pressure, we calculated the equilibrium point, we found the pressure of 83, and then we say, well, now let's use that pressure to calculate the new CT. And there was some variation from 42,000 to 42,500, but it's not much to make any big effect on the equilibrium. And then the last part that we already discussed, we want to calculate pressure along the tubing, and we have to discretize, create small tubings, and solve the tubing equation in each one. Any question? Many questions? But that's why you have the home exercise to solve and clarify them. Huh? You have questions tomorrow.